Okay, good afternoon. This is the first introduction to geophysical flows. I believe most of you are engineers, so that's why it's just a, I just have put two of these pictures. One is the Curiosity, which landed in Mars in 2012, and the other is InSight, which just landed on 26th of November. And for these landings, obviously there is a lot of mechanical engineering, but there is a lot of atmospheric sciences too, because you have to understand how to make it land. So, so that's kind of an appeal to the students of engineering to pursue a career in geophysical flows or geophysical fluid dynamics, because it is not necessarily that well taught in India. There are very few places where you have a dedicated program. Just learn from these from elective courses. So, as you see, my name is Anirban Guha. I am an assistant professor here. And some motivational pictures. The Jupiter and the Great Red Spot. I am quite interested in the red spot, and that's why I have it's in the focus here. This is not something you will like a lot. This is tsunami, but obviously it is another thing which I am quite interested in. Why these waves? Is it possible to? So there has been quite some amount of research on whether, these large amplitude waves, it is possible to get it reflected back. It's quite in the theoretical paradigm, but still these dangerous waves, whether it is possible to reflect it back is good enough. It's thanks is something which people do work on. Now, this is my hometown, and we experience this a lot of tropical cyclones, and again another problem of interest in geophysical fluid dynamics. You get a lot of rain because of that. Not here in Kanpur, but more in this eastern coast. And this is a picture taken from NASA. This is the Gulf Stream and the sea surface temperatures and these beautiful vortices, which comes from NASA's Perpetual Ocean video, shows how detailed the ocean is, and obviously it's a playground of waves and vortices. And if you are interested in fluid dynamics, why not pursue something in these areas? Okay. So, I will just have some videos first, and then so these are not completely simulations. It is a mixture of simulation and satellite data, right. So all kinds of currents you can see from here, and yeah, the one in Africa, the one now will slowly go into our part, right, and there where it ends. And obviously, as I just mentioned, it's a playground of waves and vortices.
Can I just make one comment?
Yeah.
This shows so beautifully is how important topography is in all of this. Most of those flows are topographically.
Yes, topographically first. Yes. Most of these flows are generated by topography, and to some extent we will talk about the topographic generation of not exactly these, but of internal gravity waves in the tomorrow at 9. So, yeah, the roughness of the seafloor is not flat. It's probably you are aware of this, that because of these undulations, a lot of these kinds of things and different kinds of flow features are generated.
So is that topography, do you mean the sea floor or the boundaries of the continent?
Both.
Both. The seafloor varies, but then it comes up to zero.
Yeah. And this is something which I'll start today, that this is kind of you can think of it as a lake, and a parabolic lake, and these are basically internal gravity waves, interfacial gravity waves rather, and this only occurs because of the small density difference between this one is the warmer water and this is the colder water, and if you just assume that you just tilt this parabola, and that creates a disturbance, and that causes this kind of a seeshing, and that causes a lot of mixing in lakes, and this is similar kind of a behavior is true in oceans also. So these are just some basic.
So is that a simulation?
This is a direct numerical simulation. Okay, this is a direct numerical simulation. And coming to topography, this is the Indian Ocean, at some part of the Indian Ocean. These numbers are not really visible, but it shows 27, 28. I mean, you should add 1,000 to it. Okay, so so this is the depth. So something goes like 6,500 meters, I believe, and a distance. And the main point here to see is that the density of ocean is not constant. Probably most of you deal with in engineering density constant, or when the density varies, it is compressible. So in oceans, when we talk, when we discuss geophysical flows, it is somewhere in between. It is still incompressible, but the density can vary. Okay. So the density at the top is, say it's like 1000 kg per meter cube, and the bottom says 1030 kg per meter cube. Now if you assume the density to be constant, you won't be able to get these kinds of waves. Okay. These waves, whatever you get, is because of this small density variation. Okay. Now if the red and blue are the same, you do not get an interface, you do not get anything. It's like a constant density fluid. So the importance of this small density variation is something which we will be discussing today mostly, and as Professor Huppert will go into this gravity currents, where it is also very important. It's all about this density difference that causes this. Okay.
Can I just add one thing?
Yeah.
What you said is absolutely correct.
Yeah.
That density is not constant. That's despite a huge amount of mixing of fluid in the ocean.
Yes.
A lot of ocean mixing, but it still remains
Ye-
stratified.
Yes, even after, I mean, most of these mixings are, so even after there is a lot of mixing, which the mixing is mostly caused in the upper layer, where there is enough amount of shear that causes an overturning, and which you can kind of see here. So this is kind of the mixing. So this simulation was not exactly done with shear, but as you can see that the wave breaking is happening, and that kind of causes the layer, the interface to broaden. So there is a good amount of mixing, and then then it will again slowly with time will revert back to the previous to the state which you saw at t equals to 0. So there would be mixing, and still, I mean, it is not the mixing which will cause a full overturning that happens in lakes. That does happen in lakes at times, not in oceans. In lakes, some of the lakes there is a full overturning.
You can get solidification of ice at the surface,
Hmm.
which leads to heavy fluid that drops down, and that does then go from the surface
Yes.
down to the very bottom and goes up north. So you can have
Right, right. So these are most of these introductory videos, and then I'll just go to the blackboard and do so why these things happen, just some introductory things we will go into it. Okay. Given that most people here are from engineering background, I will first start with a pulley problem. Okay, and then slowly go into how to include density stratification. We'll go into oceans starting from a pulley. So the first thing, we will consider this problem, which probably, and okay, and most of you have solved this problem, right? There is nothing I mean, it's very basic problem, but let's just revisit this problem. So tell me, what should I write as the equation of motion for this M1? Is it okay? Right? And is this fine? Right? So, this heavy guy is going down and this is causing this to go up, right? And we simply, so let it be 1, this be 2, simply add the 2, you get the T gone. So, M2 minus M1 G equals M1 plus M2 A. So, A is M2 minus M1 G times M1 plus M2. Okay. Again, something is nothing a surprise to you. Okay. Now, we will just assume that let M2 minus M1 define as delta M, which is, let us define it like this, and we will assume that delta M by 2 M1 also holds for M1 is epsilon, which is much less than 1. Okay. I mean, this mass is just slightly heavier than this, okay, just slightly. Okay. So, okay, let us write in English, M2 slightly heavier than M1. And so, what is going to happen? We will again revisit this equation 3. So, A, I will write delta M, delta M1 delta M divided by M1 plus M2, but M2 is M1 plus delta M. So, 2 M1 plus delta M. Right? Did I miss the G? Okay. Let me make the epsilon nicer. Okay. So, which means that A is epsilon G 1 plus epsilon to the power minus 1, which is epsilon 1 minus epsilon plus dot 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 G. Right? You are with me or you are lost? Okay. Therefore, A, as you can see, is epsilon G plus some order epsilon square quantity. And as we know that epsilon is a small quantity. So, order epsilon square is even smaller. Now, if you from the very beginning assume that delta M is 0 or epsilon is 0, then you do not have any, it is the static system, right. However, if you allow M1, M2 to be slightly greater than M1, then you have a dynamics, okay. And that is something very important, because now you now have an acceleration. The important point is the acceleration is far smaller than G, right. Okay. Which you see in these interfacial waves, which the red and blue thing, which the mixing happening, the waves which were traveling cannot travel at the speed of surface gravity waves, which you see on the surface of the ocean. They travel at a far lower speed. Okay. So here just important thing is, we do not, there is no need to take into account of all the higher order terms. This one is good enough. However, if you do not take epsilon, then you do not get anything. Okay. So this is what is the fundamental understanding of Boussinesq approximation. So, which I will go into. Okay. But even before I go into that, let's see that we have got this, and whether we can get this again from equations 1 and 2 by making an approximation. These equations are not approximate, these are exact equations, but let us now do an approximation to equations 1 and 2. Let us call it 1 prime as t minus m. So, let us assume that this is, it is m1g and this is m2g, but I will assume this is m1a and this is also m1a. Okay. I am not going to make any assumptions on the left hand side. m2g minus t is m2a, which I will simply write as m1a. Okay. Here goes the approximation. I will call it 1 prime and call it 2 prime. Okay. Now, I simply add these two equations. You have m2 minus m1 g as what is coming out to be 2 m1 a. Therefore, a is m2 minus m1, which is delta m by 2 m1 times g, which is nothing but epsilon g, right. So, this is, call it, let us call it this one 3, this is 4, call it 4 prime, maybe 3 prime is non-existent, maybe you can call this one as 3 prime. Okay. So, in other words, there has been something done here. What this one is telling us is effect of density, this is mass, but I can just assume that you divide by volume everywhere. Density variation neglected in the inertial terms, in the inertial term. Okay. The fact that m2, you remember that m2 is m1 plus delta m, right. So, delta m is a small number in comparison to m1. In the denominator, you can neglect delta m in comparison to m1, but in the numerator, if you neglect that, then you get nothing. Okay. So, that is the whole idea. Okay. And this, I think, the Pulley problem can get you interested in, I mean, otherwise teaching geophysical fluid dynamics to engineers is difficult, because you do not have the background, it becomes difficult. It was difficult for me too, because I am also from engineering background. Okay. But this is what you get, you relate to what you have done. Okay. So, you see the problem that where the approximation actually comes in, and then you get what you really want. Okay. So, now from the Pulley, let us go into the yeah.
Sorry, do you
Yeah.
mind if I?
No, okay, please.
I think this is beautiful. I've never seen this before, but the line I would say
Yeah.
that you've shown so nicely
Yeah.
is when m1 is equal to m2, nothing goes on. It's boring.
Yeah.
M2 needs only be a little bit larger than m1, and you really have motion going on.
Absolutely, absolutely. So, m2 needs to be, as been very articulately mentioned, m2 needs to be little larger than m1 to get the motion going on. If it is a lot larger than m1, then this approximation is invalid. So, this approximation is this, obviously we have made this approximation, the so called Boussinesq approximation, otherwise the approximation is invalid. Why this approximation? In oceans, density varies a little bit, that is the motivation. Okay. Now, pulleys are not the real motivation, pulley problem is for getting you hooked into this problem. Okay. The interesting problem is about oceans. Okay. Fortunately, I don't have color chalks. No, there are, but these are not very useful. Let me see. Okay. So, can we go into fluid mechanics now? Any questions about this whole thing? Please feel free to ask. No questions? Okay. It's exactly like my fluid mechanics class.
I have a question.
Yeah. Yeah.
So you say that the internal waves are so much slower
Hmm.
than the surface waves,
Hmm.
but an internal wave will provoke a surface wave, will it not?
An internal wave won't, I mean, usually it's difficult to, internal waves don't exactly provoke a surface wave, but when you have two layered flows, you have both internal and external modes, which means that if you have density being like this, rho 1 and rho 2, okay, and this is air. So, if you draw the dispersion diagram, so it is not like you have two surface waves, you have in total 4 solutions of the system. So, 2 are of these external, which is kind of like root GH if you go here, and 2 of these are internal modes, which are more of the what the modes of this internal coming from the internal dynamics, that kind of asymptotes to the internal interfacial waves. So, these are like the 4 solutions, because the 4th order dispersion relation which comes out from this. And so, any disturbances here that can so I would say that it is mostly what a surface wave can in general trigger interfacial disturbances more often than what interfacial waves are known to have weaker signatures on the surface. There could be, but they are weaker. Usually it is very difficult to detect. I do not know much of this work.
Oh, okay.
I know that so internal gravity, so internal turbulence, people have seen that if there are internal turbulence here, that has some surface signature. That has been by Peter Diamandis, there is a work by Peter Diamandis, but not exactly that much. Internal gravity waves do, which has been a part of my work, which is like internal gravity waves hitting the free surface gives rise to some modes that travel with frequency of the M2 tide. That is detectable, but not exactly these interfacial waves. Yeah.
So do you
Yeah.
mind if I interrupt?
Yeah. Sure. Go ahead.
Another way of putting this is to say the impedance ratio is
Huh.
large,
Huh.
so that it's quite easy for a surface wave, and especially surface sloshing,
Yes.
that might have against a
Yes.
barrier or
Yeah.
a wall to produce internal waves.
Yes.
And what hasn't yet been said, and I don't think this analogy will lead to it, but I may be
Huh.
wrong, is that the amplitude of an internal wave,
Yeah.
because there's small density,
Density.
can be
Much,
much
much.
larger.
Yeah. Yeah.
We had 100 feet internal.
Absolutely. Absolutely.
Luckily, we don't have free surface waves that high.
Yes. Yes. So those interfacial waves can have a very large amplitude. Okay. Which usually we don't. I mean, surface waves. I mean, how much it could be, like a few, not even a meter or something. Interfacial waves can be as deep as 100 feet, 200 feet. Interfacial waves have been observed.
So where is the signature of internal waves?
No, we are saying that the surface signatures of is being said that the interfacial, so the surface waves can be like something like this. So it is more or less something of this sort. So there would be some signature here, but interfacial waves, even when it goes like this, the surface area is nearly flat.
Even though they have such large amplitude?
They can, so that's how it, even though they have such large amplitudes, because of the density ratio it comes out to be, the surface remains nearly flat. Okay. So, okay, let's go into the fluid mechanics equations. How many of you are aware of Navier-Stokes equations? I am not talking to, okay, most of you are aware of, okay. So, are you going to, So you are going through the, will you derive the Navier-Stokes in you won't, right? Okay, good.
You can.
Yeah. No, I am assuming that people know Navier-Stokes. So from there, otherwise it will be. So please help me write the conservation of mass. What? Some people just took my VFT course, viscous fluid theory.
I wrote it earlier.
Is it okay? Is it fine? Okay. So rho density u velocity. Okay. And ddt you know is material derivative, right? Now the conservation of mass, can you do some scaling analysis of this? What is the scale of this? Say assume that u, capital U is my velocity scale and some L is my length scale. Can we do some scaling analysis of this? Okay. Okay. So my point is, when density varies, but the variation is small, we can simply assume this to be divergence of u is 0. Why? The assumption comes from the fact that density is materially conserved. Okay. What does it mean? It means that say you have an ocean and density is varying something like this. So density varies with depth. So you have a parcel here, okay. Say its density is 1030 kg per meter cubed, right? And as the parcel keeps on traveling, and assume that there is no diffusion, okay. As the parcel keeps on traveling, its density remains 1030. Okay. So the density is materially conserved, although the density is not constant. Okay. Okay. This is one of the most fundamental things when people sometimes assume that the whole idea is only for density, for constant density flows. It is not necessarily true. You have a slight, you can expand it slightly. Okay, it is true. So the times, if you just right. So this flow, I mean, if there is a diffusion, you need to add something with the diffusion of a scalar. So this is not conserved. So you have to add a diffusion of the scalar, because density is a function of temperature and salinity, and they will diffuse with time. So with a so if you take a long time scale, obviously it is not going to hold true, but we are not assuming such a long time scale.
Can I ask another question?
Yeah.
So earlier you said that when you have your density gradation mix, it will reconstitute itself.
Yeah, if there is so assuming that you have a shear layer profile like this, and you have some density like this, and you have some mixing going on. So it will just become like that, right, with time.
Then, so let's suppose that shear ceases or that mixing ceases. Then the density profile will again become gradually more abrupt. Is that not true?
So density profile. So the density from here, now it has become something like this. Then yeah, with time the density profile is going to change. I mean, it is not the only process there.
No, I guess the question is that if you were to stop the shearing,
Huh.
would the gradient recover to be what it was earlier? Or
No. So the grade, if you So the shear has, so if there is a density like this, and you have a shear profile like that, and since the shear has caused an overturning, okay, so this will give rise to some billows like that. Okay, these billows are going to cause even bigger billows by pairing. Okay, that is going to break down into turbulence. So that is going to thicken, becomes the length scale is going to increase.
Okay, now
Okay, and then you have,
let's suppose the shearing stops.
okay.
Does that density profile recover?
No, it doesn't. It's not like an irreversible, it's not like a reversible process where you just start something and then it just recovers. Once the motion, once you have a wind
Then I
event.
misunderstood
Yeah,
something earlier.
okay. So if the wind event starts and it causes the motion to set up, it just triggers, and then you have turbulence and mixing, and the density profile keeps on broadening.
I'm confused with your comment earlier that there is internal motion churning of the ocean, but the density profile remains unaffected.
I didn't say the density profile remains unaffected.
Largely unaffected.
Oh,
No.
No, well,
No.
because we're just looking at one
Yeah.
aspect. What happens if there's an internal wave and it can come and mix things or salt? But of course, what is happening in the real ocean,
Yeah.
which is not happening in the simulation, is that there's heating and cooling.
Yeah.
So that plays a role.
External
Yeah.
forcing which is
So
being
there's
there.
Yeah.
external forcing.
Yeah.
And there may even be a slight control from heating from below.
Yeah. Yeah,
geothermal.
geothermal heating, yes, yes, yes. And the other thing is that this is confined in the pycnocline, in the region where the density is sharp. So the ocean is like 4 kilometers. Largely in the bottom there is nothing happening, and it's mostly in the upper 100, 200 meters where you have interesting stuff going on. But so if someone says that it's largely unaffected, I won't say it's wrong. It's true, because
To me, the clarification was that the external constraints maintain that profile.
yes, the external constraints.
Because of this.
Yeah, the external constraints maintain that profile. Yes, yes.
Can I just sort of come
Yeah.
and say, for the first time,
Yeah.
I think what you've said is not quite right.
Hmm.
And there's a famous story
Hmm.
that Stommel, who was a very
Yeah,
famous
yeah,
English
yeah.
oceanographer, invented what a called, it's not Stommel, sorry, Swallow,
Okay.
invented swallow floats.
Hmm.
And these were floats that you could put in any part of the ocean and they'd stay there because they're more compressible than seawater. You can look at the stability. So you could put them down, 1,000 metres, 2,000 metres. It was done, I think, in 1956, might be out by a year or so. And everything was believed to be, as you'd said, very quiet. So they only had sailing boats in those days available to them. And so they thought they'd track them by sound with the sailing boats. It was either a disaster or a great success because the swallow floats shot all over the place. There was lots of very rapid motion at depth 2-3 kilometres into
Yeah.
the ocean, and they lost them pretty quickly.
Yeah, but that's because of internal gravity waves.
Because of everything.
Yeah, yeah. So yeah, I mean, I don't want to go into that, but internal gravity waves are known to transfer energy to the higher and higher modes. So they do cause turbulence, which is now well understood in mid-Atlantic ridge where they have a lot of turbulence. But in general, I would say that if the topography is mild, okay, if the ocean's bottom is not varying too much, you won't get a lot of internal gravity waves. They are mostly generated by rough topography. So it also, I mean, there are lots of factors coming in. So obviously, obviously there are interesting things happening deep down in the ocean. But if the region is, if there is not some interesting topography there, it is very difficult to see interesting features. For example, in the mid-Atlantic ridge, you see very interesting features. There is a paper in Science, but the same near the Brazilian basin, which is just a little bit, so it's a left of it, you see almost nothing interesting. It's very, very flat. So it depends on a lot on topography also, that whether you have interesting features or not.
Because the topography can be influential thousands of kilometres downstream.
Yeah.
You might have a topographic effect that leads to a vortex, basically.
Right.
Just just like you have hills.
Yeah.
Not near here, but I guarantee there's weather that you see due to hills, the Himalayas,
Right.
which are a long way away.
Yeah. Yeah. Okay. So coming back to the conservation of mass, we just so the assumption here is that the density is materially conserved. As you understand that there is no, so if you have assume that it's the that here the density is 1030, here the density assume is 1010, but as this one moves, I mean obviously if it moves so slowly that diffusion takes you have to take diffusion into account, then obviously this is not going to hold true. But if you assume that it is at a faster, somewhat faster time scale, so that you bring this parcel from here to up here, okay, its density is going to remain 1030. It is materially conserved. Okay. And now that will have consequences that will give rise to some waves, but that's different. The important part is that density is materially conserved. Okay, that's what we will start with.
Is it simply because the density variation is because of variation in salinity rather than variation in pressure?
So yeah, I mean if there is a density, so density variation, see if the density, so we are not interested in compressible flows right now. If you are thinking of say adiabatic or something, something PV to the power gamma, something like that, it is not no.
Simply that the variation here in the ocean,
Huh.
variation in the density is because of salinity rather than variation in pressure. Is it
Salinity and temperature rather than pressure, yes. I mean I won't say that it is completely incompressible, obviously there are some amount of compressibility, but which we ignore. Okay. It is not like there is any fluid which is completely incompressible, no, but we ignore that. Okay.
Another way
Yeah.
of saying that is the motions in the ocean are very slow compared to the speed of sound.
Yeah,
And that's
yeah.
basically it.
That is again another way of saying Boussinesq approximation. In Boussinesq approximation, what we have done, it's good that this point has been brought. We filter out sound waves. Fast waves like sound waves are filtered out. What remains are the slow moving or the internal gravity waves, right? That epsilon g, these are slow waves. Okay. Okay, so the conservation of mass, simply that the equation 1 is divergence of u is 0. Now let us for simplicity just look into the 2D equations. Maybe we will also think of 3D. Okay, just first let's the 2D Navier-Stokes equations. 2D Navier-Stokes equations. So you have rho du dt. Please help me write it. I have written it so many times. Minus del p del x. So this is my coordinate system. Okay, x, z, and this is my g. Okay, del p del x. I will assume that the flow is inviscid because viscosity is something which are right now we are really not bothered about. Okay. Okay. And what about the, so this is my x momentum, and what is my z momentum equation? Minus some rho g, right? Okay. Now the next thing I will assume is I will write pressure, which is a function of x, z, and t, as some p hat z, a mean, okay, and some p prime x, z, and t, and similarly density as some mean density Oh, I wrote x, y, and t. Thank you very much. Okay, so this rho bar means what? Rho bar is this. Okay. So how you take the mean? Okay. Now there is no mean flow. We are not interested in any mean flow right now. Okay. So these whatever your u, you can write as u prime and w also as w prime. Okay. So let's write it rho bar plus rho prime, right?
U dash and W dash are fluctuations.
U prime and w prime are fluctuations, yes.
So these are equal. We are considering
Which are equal?
this U and U prime. Both are equal.
Oh, u and u prime are equal because it is the, so the mean is 0. Huh. And this is also, there is no mean, okay, 0 mean. Okay. So we will write this as, and then you have del u del t now del p del x will be minus del p bar del x, which is 0, minus del p prime del x, right. This is the first equation. Okay. And remember what we did when in the pulley problem, we understood that any variation in the inertial term is not important. So remembering the pulley problem, we had this m1 plus 2m1 plus delta m, whatever we had, we assumed it as 2m1, delta m is gone. So that is the same thing which we do in the Boussinesq approximation. We do not use this rho prime anymore. So this is approximated as rho bar, whatever you have. So this is nothing but I am just writing the du prime. So this is nothing but du prime dt equals minus del p prime del x. Okay. So this is now my equation 1. Let not be equation 1. Let this be my equation 1. This is 2. And similarly, what would happen if we write the z momentum equation? The z momentum equation would give me, so this is my x momentum, and my z momentum equation would give me rho bar plus rho prime, and it is more interesting, dw prime dt equals minus del p prime del z minus del p bar del z minus del p prime del z minus rho bar g minus rho prime g. Okay. Now what I have not mentioned yet is that whenever we do some kind of an analysis, we assume a base state, right. Say you want to know that you have a ball, okay, in this kind of a concave shape, you give a small push, what is going to happen? So this is your first your stable, that's your equilibrium point, whether it's stable unstable, that is the next, that is you will find whether this is stable or that is stable, whatever. But you need to know that this is a configuration about which you give a perturbation and you try to understand what comes out of it. Okay. So here we will assume that the base flow, the base, don't call it a flow, do call it a base state, because there is so called no flow, base state is hydrostatic. Which is understandable, right? The ocean in general, if it is under a hydrostatic equilibrium and you give small amount of disturbances and you want to see what happens. Okay. So if it is hydrostatic, what does a hydrostatic base means? It means that minus del p bar, I shouldn't be writing actually del, I should be writing d, but okay, minus rho bar g is 0, right. That is the condition for hydrostaticity. Okay. So, here I should not be writing del, I should be writing d, because p bar is only a function of z. So, these are gone. Okay. Notice what I am going to do in the next step. I will throw away rho prime, because it is multiplied, it is in the inertial term. Okay. So, I will simply have rho bar dw prime dt equals minus rho prime g. Okay. And this is where the Boussinesq approximation becomes so important. Okay. I have rho bar plus rho prime on the left hand side and rho prime in the right hand side. I neglect rho prime on the left hand side, just as we did in the pulley problem. Okay. So, in comparison to rho bar, rho prime is nothing. Say that this is 1000 and this is 3, I can neglect 3 in comparison to 1000, right. So, that is why it is rho bar, but here there is, it is being compared with 0. So, if you throw away this rho prime, you do not get any that kind of a fluctuation, you do not get any internal, you do not get anything about the fact that density in the ocean varies. The whole idea that density in the ocean varies is kept here, it is contained here, and that is why we cannot throw it away. Okay. So, very simply then finally we will write the equations of motion as, yeah. Oh, I forgot my del p del z term. So, this term is there, thank you for pointing it out, minus rho prime g. So, my conservation of mass gives me x momentum equation is going to give me okay, and my y momentum equation is going to z momentum equation is going to give me okay. Now, this rho bar, we assume it to be, this rho bar is something like the average of in oceans, how much is the variations, you are already do not really need any z variation here, you just replace it with any number between 1000 and 1030, among which 1000 is a reasonable number. Okay. So, that is why you assume that rho bar is something like rho naught, which you can assume to be 1000. If you do not like 1000, you can put something other, some other number, it does not matter. So, usually I will write, instead of rho bar, I will write rho naught and put it there. Okay. Okay. So, these are my governing equations for density stratified flows. So, 2D governing equations for okay. Is this clear, or any questions on this? Can you derive it yourself? And any questions in the derivation, just let me know. Okay.
assume that the velocity fluctuations are small.
Yeah, nowhere I have assumed that the fluctuations are small, because I am not really looking right now at small amplitude waves, which I will look into in the next tomorrow, where we will be doing more of an internal gravity waves with a small amplitude. But these material derivatives, everything, they are these. So we have a departure in some way. Yes, it's we do not need it to be really small. I mean, very small means that we are actually assuming that it is linear wave. We are not actually just in linear theory.
But the base state is static.
My base state is static.
That is why you don't need small.
Yeah.
Comparing to zero.
That's
Yeah.
really the point, that
Yeah.
W is zero, the
Yeah.
reference velocity is zero.
Yeah.
So in some sense, the perturbations are enormous.
Yeah, the reference velocity, rather I will say the reference shear, because you can always go into a reference frame with a large velocity. So the reference shear is absent, otherwise it would have been a problem. Huh. Okay, with this, let's. How many of you remember Kelvin's circulation theorem? Or you have heard of Kelvin's circulation theorem? Anyone heard of? I just saw one hand, two hands.
They know it under his real name.
So is his real name J.J. Thomson, or what was his real name?
Sorry?
Is his real name J.J. Thomson or no?
No, Thompson.
Is Thomson, right?
And there's a stupid English tradition used to be, once you were elected to the peerage, you took another name,
Yeah.
and he took the name of the Kelvin River,
Okay.
which was close to where he was.
Okay. Okay. Before I even go into Kelvin's circulation theorem, there is something I will just like to point out, and why I am actually revisiting Kelvin's circulation theorem is important here. That say you have a container, and assume that you have put a partition here, and you have a density rho 2 here and rho 1 here, and rho 2 is say greater than rho 1, and it is open to the atmosphere. Okay. So, this is your atmosphere, right, and say this is your whatever x and z. What happens if you suddenly remove so this partition? You just think that you can do that. You can simply, in a fraction of a second, you can dissolve this partition. What would happen? There would be some circulation. So, the heavier fluid is going to go down like that, and the lighter fluid will travel up. So, you can assume, you can very well see that there is a circulation is going to get set in. So, it is under atmosphere, you can think that this is under hydrostatic balance, which means that your pressure gradient is like this, okay, and your density gradient is so rho 2 is greater than rho 1. So, rho 1 to rho 2 it will be like this. So, say assume that is grad rho, and grad. So, if I have a term like grad rho cross grad p, which is going to come, by the way, if we have a term like grad rho cross grad p, it is going to create a circulation, create a clockwise motion, a counterclockwise motion like this, right. So, this is going to go down like that, and something is going to go up. Right. So, if there is a term like that, that is going to set up a motion. Okay. So, the important point here is density stratification can cause vorticity generation. Okay. Some of you who took my course, they already know that viscosity leads to vorticity generation, right? If you have a bound flow over if you have a flat plate, you just move a flat plate, the momentum gets diffused into the bulk fluid, right? So viscosity causes that. But density is something which we do not talk about, but it is the most important thing in geophysical flows, is one of the most important things. And so the density stratification can also cause vorticity generation, is something very important, and that we will see from Kelvin's circulation theorem. So okay, I have already mentioned. So Kelvin's circulation theorem says what? If you have number 1 incompressible flow, conservative body forces. So just assume for incompressible flow density is constant. Okay. For now, I mean, we have already shown that incompressible flow may not have density as constant, but assume. So these are from Kelvin's circulation theorem, and conservative body forces. Then we have the circulation is materially conserved, right, which comes from what? So what is the definition of circulation? Right. Now you understand that what does it mean by conservative body forces. So if I am writing the Navier-Stokes equation, I can write it as something like rho du dt is minus grad p. So let us take density here. So you know that conservative forces can be written in terms of a potential, right? That is what the whole idea of conservative forces are. So just do a d gamma dt, it gives you du dt dot dl u dot d of, say this dl dt, which is nothing but, so let us call it delta L dt, which is nothing but your du. So this gives you, I will just make use of this. So L is a vector, right? It is difficult to write it here. Let us write it in 2 terms. Okay. Can I erase this board? Is it okay? Is it okay? Can I erase this board? Okay. So d gamma dt comes out to be, so the first term is cyclic integral of, so rho is assumed constant, you can take out of the integration, grad p dot dl is what? Grad p dot dl is what? dp, and if you integrate over a closed contour, it is 0, right. So this becomes 0, and grad phi dot dl, so this is nothing but d phi, and integral over a closed contour gives you 0. and similarly you will have something which is so you have u dot this, so this gives you something like du. I will just write it as du, something like half of something like u square. So, this also goes to 0, and that is how Kelvin circulation theorem is valid. Okay. So, d gamma dt is 0, circulation is materially conserved. Okay. So, that proves the Kelvin circulation theorem. Now, everything else is okay, we will simply relax this one, which is actually not true in this case. If density varies, so you have taken the density outside because density is constant, which you cannot do if density varies, right. So, this thing 1 by rho grad p, you took the rho outside because you have assumed that rho is constant, but rho is not constant in oceanic flows, and therefore, Kelvin circulation theorem is strictly not valid. Okay. So, what else can you do with this? What is d gamma dt? What happens if you have if you have right. If you cannot take rho outside, it will remain like this. Okay. So, this is what says that the, so it is not like so Kelvin circulation theorem is not valid in stratified flows. Okay. The way to see it, I would say, is something which we already did. We derived the whole Navier-Stokes equation. We will again go into the Navier-Stokes. Now, not in the like I won't write it in component form. I will rather write it in a vectorial form, so that an important part which is known as the baroclinic torque becomes evident. Okay. So, again I am writing the Navier-Stokes equation number 1 du dt, no, just write the Navier-Stokes. So, just write something like that, it does not matter. Tell me, how do we get the vorticity equation? Curl. So, what happens if we take the curl of this equation? I should have 1 by rho and rho prime by rho 0. So, assume that whatever these equations are, so this u and these are all perturbation quantities. It is not that always we have to write prime. So, if you take a curl of this equation, what do we get? Curl of this equation. What was the last equation number? 4, 5, 6 something. Remember? Huh? Switch to Greek or Roman? Huh?
It will be 4.
It will be 4. Okay. Okay. I do a curl of 4. Not the number 4, it will be 0 then. What happens if you do a curl of the momentum equation? If it is a 3D momentum equation, what happens? You have a vortex stretching term, right? Stretching and tilting. In 2D, you do not have that. You know, I am assuming that you know that. Okay. So, I am doing a 2D thing, and because it is 2D, I will just simply write d omega dt. And curl of grad p prime This is what, 11? 0, okay, good. And what about this one? So, omega, let me define what is omega, del u del z minus del w del x, okay, 2 dimensions. So, just okay. So, I am just becoming a little hand wavy here because I am using a vector notation and omega is actually a scalar, but you understand that if you take the curl and you just do the cross differentiation, that is gone. Okay. So, so the vorticity equation is simply g by rho naught del rho prime del x. Okay. And this is something which is known as the baroclinic generation of vorticity. So, vorticity is being generated by density, by these density perturbations. Okay. This is the simplest way in 2 dimensions to write the baroclinic generation of vorticity. Okay. In case you do not like it, the simplest one, you can derive it in another way. You can simply write rho du dt in full equations as grad p plus some, say, rho prime g k whatever, divide by rho. So, it is 1 by rho, right, and rho prime by rho, full rho. Take a curl of that. So, curl of 1 by rho grad p will give you minus 1 by rho square grad rho cross grad p, okay. And that grad rho cross grad p I have here, which basically shows the direction of the motion. Okay. The fact that if you open this this gate, the heavy fluid is going to go down and the lighter fluid is going to go up and cause an anti-clockwise circulation, that grad rho cross grad p comes from, if you take the curl here, and that is basically in 2 dimensions contained here in some way. Okay. So, that is what is very important now, and mostly I have kind of covered that that Kelvin circulation theorem is no longer valid because density is not conserved. Kelvin circulation theorem gets some additional term, okay, and that causes a generation of vorticity in 2 dimensions. If you do not have viscosity, usually you think that vorticity is conserved. That is no longer true if you have density stratification. This stratification gives rise to vorticity generation, and that is what is very important for these waves whatever you see. These are all caused by some kind of a vorticity perturbation, right. And at this point we have not assumed that these perturbations are small or large. There has not been any such assumption. Okay. These are perturbations, mean plus perturbation, and we have separated the 2 things out. Any questions? Let us go through some. If you have questions, just ask me, we can keep on discussing. Otherwise, I will start something on internal gravity waves, but let us, if you have, I mean, this is the first thing what is about Boussinesq approximation. You understand that what is Boussinesq approximation? You throw away the small density variations in the inertial term, but you keep it when it is multiplied by g. In the gravity term you keep it, but in the inertial term you throw it away, because by throwing it away you do not lose much information. The information you lose is order epsilon square, which is anyway very small. Okay. So, that is why Boussinesq approximation is a reasonably good approximation. Okay. What it does is been mentioned by Professor Huppert, that Boussinesq approximation not only preserves incompressibility, the effects of compressibility like the faster travelling waves like the sound waves are thrown away, but the slower types of waves which are very important for oceans like the internal gravity waves are kept. But if you assume density as constant, everything is not, you won't get any dynamics, right. So, that is a very important point. We just next we have visited the Navier-Stokes equation, and you have seen that how Boussinesq approximation is actually applied, okay. And then the vorticity equation, which is probably the most important thing when you are applying Boussinesq approximation. I mean, some people obviously do in vorticity equation captures it very succinctly. You just have a one term in the right hand side in 2-dimensional xz plane, it is just one term on the right hand side, it captures it very succinctly. That vorticity is being generated, omega is the vorticity being generated because of density perturbations, okay. And also you have seen that the Kelvin circulation theorem is not valid if you have density stratification, okay. It is not materially conserved, which is again another way of writing that, okay. You can multiply that omega by dA, omega dot dA integral gives you the circulation, you can do the same thing, you will end up there, okay. Any questions? Yes. If you have viscosity, you so see probably have erased it. Kelvin circulation theorem is not valid when you have viscosity. It is only valid when you have conservative body forces. Okay, that is the first thing. So that is one. You say that rho is constant, and the second thing is conservative body forces. You can see that the body force is in grad phi. That grad phi dot dl that encapsulates the conservativeness of the body force, any body force, I do not care, it has to be conservative. Okay. Yeah.
You said that we are not making any assumptions regarding the perturbations. Are you saying that we are not making the assumption regarding the amplitude of perturbations, like in fact in small or higher amplitude?
By which I mean there is here there is no need to invoke that rho prime we have said, but whatever the u prime or omega prime are, we are not saying that these are small, we have not assumed that this material derivative is linearized material derivative, those things we have not assumed.
Right hand side, the right hand side part we are neglecting the epsilon square term, exactly, epsilon square term.
Right.
But then again that itself underestimates that whether we are taking the perturbations of finite amplitude or not. Right?
No, it does not, because order epsilon square, see epsilon the order epsilon square of rho prime does not say that you cannot have nonlinear waves. You can definitely have nonlinear solitary waves, interfacial solitary waves, you can definitely have in Boussinesq approximation. It does not say anything of that sort, okay. Nonlinear waves, nonlinearity of waves come from the wave's steepness. The epsilon is different from this epsilon, which is about Boussinesq approximation, okay. It is about the wave steepness, whether you can definitely have a steeper wave, you can allow that, there is absolutely no problem, okay.
What about the P prime? P prime also has epsilon square term. Like
You have a
P prime is the perturbation, right? Still have order epsilon square term. We are neglecting that word.
I mean, what do you mean by so here the assumption is any order epsilon term which has been neglected are the terms. So for example, you had some order epsilon term, you had a density, so rho bar or rho 0 plus some epsilon times this, right. You have neglected this in terms of so here you have taken that, and when you expanded you had something like 1 by epsilon to the power minus 1, and you have expanded it and you have neglected it, right. So whether that epsilon whatever it leads to, whether that is important for nonlinearity, for nonlinearity of the waves, no, they are not important, okay.
When the
that is, so this approximation fails if your density stratification is not small. Okay. However, I have gone through revisited the Boussinesq approximation very recently. It turns out that the air water interface, right, the surface gravity waves at the air water interface, the deep water surface gravity waves, their phase speed is given by root AT GK, right. AT is the Atwood number. Okay. I think it is AT GK by 2 or whatever you can define, but it is proportional to root AT GK. Now, if you take AT as 1, you get the surface gravity waves, and if you take AT as epsilon, you get the interfacial gravity waves. So, it means that for short waves it does not matter. I mean, for short waves a large density variation, so rho 1, so this density variation can be large. So, air water means the density variation like is 1000, 1 to 1000, right, that is still okay, but the long waves fail. Okay. So, the length scale is very important. It is that it has been also mentioned previously for compressible flows that the length scale also matters. It is not just the densities variation, but those will be more of the advanced topics for this one. But as far as I can tell you is that not just the density, just the fact that Boussinesq approximation means that the density variation is small is something I at least have questions, and I have just had a POF paper on that. So, as you can see that the phase speed it does not matter, if it remains the same, you make the Atwood number go from 0. So, Atwood number small is Boussinesq, Atwood number 1 is definitely non-Boussinesq, but for surface deep water surface gravity waves you change Atwood from 0 to 1, it remains Cp. I mean, it is the same formula, the formula should be invalid. It is invalid for long waves, it is not invalid for short waves. Okay. Yeah.
Addendum to that,
Yeah.
which comes very much to Jim's interest. Orbital differences, but now when you have sand-driven blast, or blast not quite the right word, the gravity can't, and I'll talk a little bit about that, but sand-driven, so that's where the grains come in, then the density of the haboob, as it's called, can be considerably larger than the density
Yes.
of the air.
Yeah.
So then non-Boussinesq effects can come in.
Yeah. So, yeah. So, I believe that it is basically a there shear. So, in haboob these density currents, there is also a shear at the interface between the interface between the density current and the ambient. So, that shear actually is very much responsible for making the Boussinesq approximation invalid. I do not know much about turbidity currents, though I do not know whether Boussinesq approximation is valid there or not. People do apply Boussinesq approximation, I have seen.
Well, the other part of the answer is for most things that the Boussinesq approximation works.
Yeah.
You can definitely do experiments in the laboratory where you make M1 considerably different to M2.
Yeah. Yeah.
Example,
Yeah.
so that they're non-Boussinesq effects. And then what I'd say is those people who do those sort of experiments think that non-Boussinesq effects are very important. Those who don't do those sort of experiments think that it's not that essential.
Yeah, I mean, in atmosphere sometimes the non-Boussinesq effects become important. That is what in atmospheric sciences people go into these non-Boussinesq or rather anelastic approximations, which are slightly more complicated than this, not relevant now. We will be mostly focusing on Boussinesq approximation, and so so it is a right point to conclude. I will say that please go through these details. It is not much, because in the next tomorrow we will go into internal gravity waves. Right now we have not talked, we have mentioned waves, but have not gone into this how to put the wave form like the normal modes in these, and then we really want to see how these waves propagate. So, the fact that there are waves propagating in the deep ocean is very interesting, because it seems like there is nothing happening in the deep ocean. In fact, I also made the comment that there is not much happening in the deep ocean, because it is a very general comment. However, very interesting things do happen in deep ocean, and my student Shubhajit does work on that. So, it is not like I mean, waves are radiated and there are internal there is a transfer of energy. These are very, very important, and that is something which says that how the tides, the lunar tides, the solar and lunar tides get dissipated, how that causes ocean mixing is very much related to the what happens in the deep ocean. Okay. It is not on the top, it is the deep ocean that actually is very important there, and that is what we will kind of discuss in the tomorrow at 9 or 9, right.